Hello and welcome to the 10th part of the Introduction to Haskell course. We are now entering the final stages of the course, in which we'll cover slightly more advanced topics of Haskell, primarily functors, applicatives, and monads, which are type classes that each abstract some idea of programming in Haskell. So today we start with functors, so let's see what they are. Functors, as we already mentioned, are a type class, and the idea that they generalize is the idea of function mapping. So we already saw function mapping with lists with the map function, and in general function mapping, we can think of function mapping as applying a function to each element in the data structure. Maybe not necessarily to each element, but a function mapping defines for a given data structure, what does it mean to map a function over this structure? So for lists, it means apply the function to each element of the list. For other types, it could mean something slightly different. We'll see soon. Anyway, we already know the map function that works with lists, and we know its type signature, a function from A to B, a list of A's, and finally the result, a list of B's, which is the result of applying the A to B function to each element of the list of A's. Okay, so functors basically abstract or generalize this idea of the map function, and they are a class that supports the main method fmap. So here we have a class definition for functors. We have class functor f where, and then we have the type signature for fmap, and another function we'll cover soon. So fmap, we see the type signature is very similar to one of the map from lists. We have a function from A to B, and then instead of a list of A's, we have an FA. So F is a data structure. It's a parameterized data type, right? So F is some kind of type that holds values of A. And the final result is f of b's. So again, the result of applying the function a to b to f of a's results in f of b's. So very similar to here. And if we remember, the list of a's written here can be written in another way, right? We have just the list constructor, an empty list, and a, so this could be written this way as well, and it would mean the same thing. So this is just kind of syntactic sugar. And if we write it this way, then it becomes very similar to this, right? So our f here is the list constructor, and a or b is our type of elements in the list. So this way we can map functions not just over list data structures, but a wide range of parameterized types that we create. The other function of the functor class is this, I'm not sure how to read it, less than $, which is a pretty simple function that takes in a value rather than a function and replaces each element of the given data structure with that value. Okay, so again, data structure of f of b's becomes a data structure of f of a's, where each value is equal to the given value at the start. Okay, the minimum complete definition is fmap. So fmap is really the most important function that we care about when talking about functors, and that's the general idea of the functor class. Now we take a look at a type that we haven't seen before, but it's very common in Haskell. It's the maybe type. It is a prelude type, and it's used to allow specifying something that may not be there. So in general, it means it's used when something could go wrong and we want to basically sort of catch the exception and if we do, we'll use this data constructor nothing to represent an error state. That's the most common use case. Anyway, its full type definition is data maybe A, so it's a parameterized type that takes in a type of A. So a maybe could be maybe int, maybe string, maybe any other type, and it comes with two data constructors, just and nothing. So like I said, nothing represents, well, nothing, and it means something went wrong, basically. Some calculation did not work out, so as a result we got nothing. Or just A, which is simply a wrapper around a value A, so it means it's really just this value simply wrapped around in the maybe type or the just data constructor. Okay, so when we talked about function mapping on lists, we said each element, the function is applied to each element, and the result is the concatenated list of all the results. So for maybe type, that sort of apply to each element doesn't really work, because the maybe type has pretty much just one element, but it has two data constructors, so it can be either just or nothing. So for the maybe type, when we make an instance of the functor type class, we need to specify what fmap means for the maybe type, what function mapping means for this data structure. And of course, this is predefined in the prelude. I'm using it as an example. We don't need to make an instance for the maybe type to be a functor. It's already done. But anyway, so function mapping on a maybe type would mean apply the function if there is some value, if there is a just A, or if it is nothing, then simply propagate the nothing. So we propagate the error state, and we know something went wrong. So when we create an instance, we can say fmap, and the function f we can ignore if our maybe is nothing, in which case we simply propagate nothing. Or if we have fmap in the case, so we get some function that we don't want to ignore in this case, because our maybe type is just x. So we have some value x, and we can apply the function to it. And then what we return is the data constructor just wrapping the result of the function application fx. We looked at the maybe type, which is a predefined type in Haskell, and how it is made into an instance of the functor type class. In other words, what function mapping means for that type or data structure. So now the question is, how can we make our own types into instances of the functor type class? And the principle is the same. We know that functors support this method fmap, which generalizes function mapping over a data structure. So when we have our own type and we want to make it a functor, we simply need to think about what does function mapping, what does mapping a function over our type mean, and what do we want the result to be, what do we want it to do. So here's an example of a simple binary tree, a binary tree type. We define it as data tree A, where we have two data constructors, leaf A, which actually holds some value A, right? So it's a leaf node, holds a value. It's so the tree type is either a leaf or a branch, and leaves carry values, and branch by itself does not carry any value. Instead, it has two children, tree A and tree A, so left and right side. And by itself, branch does not carry any value A, only the leaf nodes carry a value. Okay, that's just this implementation of a binary tree. So when we want to make this type a functor, we need to think about, okay, I have a function, I map this function over this tree type. What do I want the result to be? What do I want function mapping to mean for this type? So we can say the normal definition of an instance functor, our type tree, where we have a function from A to B, we have a tree of A's, and the result will be a tree of B's once the function is mapped over. So first, let's take a look at the case where we have a leaf of X, right? So we have fmap in general. The second argument will be a tree of A. We know that the tree of A can be either a leaf or a branch. So first we look at the leaf, and we know that leaves carry some value X. So when we map a function over a leaf, we simply want to apply the function to the underlying value X and wrap it back into the leaf constructor. What about branch? So if we encounter a branch which we know has two children, we'll call them left and right here, then since the branch does not carry value on its own, we don't have a value to apply the function f2, but what we want to do is recursively process each of its children with the same function, right? So we recursively call fmap with the same function to the left tree, to the left child tree, and to the right child tree, and the result will be, of course, the same branch, but with all of its children, any leaf nodes in its children mapped with this function f, and eventually we'll get to a leaf, and that leaf will actually apply the function and give back the result of the function application. So that would be how we want a function mapping to work for our custom type in this case. Here we have the example of a binary tree that uses our data type tree from the last slide, and we define an instance of this tree as a branch that so the first node is a branch here, right? It does not hold any value, but instead it has two children, left and right, and the left child is also a branch, so also does not hold any value, but instead has two children. And the right branch, the right child of the root node is also a branch, also does not hold any value, but has two children. Okay, the children of the second level nodes are leaf 1 and leaf 2 for the left branch, and leaf 10 and leaf 20 for the right branch. Okay, so that's how we get this diagram. And now, since we made this type into a functor, we have the fmap available to be used for my tree, and we can take an example here where we map a function of divide by 2 to our tree, and the result is then the structure remains the same, right? Branch has it's the root branch, has two children, branch left and branch right. Each of those have two leaf node children, and now since we map the function divide by 2, the values stored in the leaf nodes are all divided by 2. So the first one from the left contains now 0.5, the other one contains 1.0, and the right side contains 5.0 and 10.0. Okay, so another thing to note, which we already know that can happen, mapping a function, because fmap accepts a function from A to B and a data structure of A's, and the result is a data structure of B's. So as a result of function application, the type of the value stored in the data structure can change. So like we see here, we had integers, but when we apply this divide by 2, and this is float division, so the result will be a double, we end up with a tree of B's, B standing for double in this case. Now a note about an infix operator for fmap. So the prelude also defines this infix operator for fmap, which is this less than $, greater than operator for function mapping should not be confused with the function application operator that we learned about before. So the function application operator is just a $, and it takes a function and applies the function to an argument. On the other hand, the fmap operator is the same as fmap, right? So given a functor f, it takes a function, the data structure fa, and turns it into a data structure of fb's by mapping the function over it. And it's simply fmap, nothing else. So instead of writing fmap, we can use this infix operator. So we can say my tree stays the same as before, and we say, okay, apply the function, divide by 2, map it over my tree, and we get the same result as before. So it's just a matter of preference what to write. If you see this infix operator in Haskell code, now you know what it stands for. Finally, we'll take a look at functor laws, which are laws that ensure that a given instance of the functor type class is valid. In other words, that the fmap method for that type is defined correctly. So there are two laws. The first one is that the identity function is preserved. Now the identity function we haven't seen before, but it's this function id, and it's a very simple function that simply returns its argument unaltered. Right, so if we say id of 1, we will get back 1. So it doesn't do anything to its argument, it simply returns it. So the law is saying that mapping this id function that basically doesn't do anything over a data structure should be the same as simply calling id on the data structure, which of course makes sense, because if mapping the id function returns something else, then it's a result of a badly implemented fmap. So which, even given a function that doesn't change anything, changes something in the data structure. So that would be wrong. The second law is function composition is preserved, and function composition we already know about. It is the dot operator that composes two functions together, and this law states that if we map a composed function composed g and f, if we map it over a data structure, it's the same as mapping the g function and mapping the f function. But of course, given that the order of the functions is the same, right? So here the composition is g composed with f, and here f map g is composed with f map f, so the order stays the same, and then the result should also be the same since the order of function application is the same. That's the end of this presentational part, where we covered an introduction to functors, which generalize the idea of function mapping over parameterized types or data structures. So now let's get into the practical part, where we'll do some exercises with functors. This practical session will be about functors, and from what I understand, the best way to practice functors is to implement the functor instances for various types. So that's exactly what we're gonna do here. And the way I prepared it is I imported prelude, but I hide the functor type class and the fmap function so that we can just have functor defined here as our class that has just the fmap method. Now we know that there is also the I don't know the name of this method, but this one that replaces all the values in the type with a given value, but we're not really interested in that. Now the main thing is fmap, so we have the class functor definition here, which is the same as in prelude, but just to have it this way. And so now if we load this file and we try to fmap some function, let's say times 2, over a list of 1, 2, 3, then we get an error because there is no functor instance for the list type, right? So we cannot use fmap. So we have to implement the instance first before we can use it, and the same for each of the other types. So let's get started with the list functor instance. For lists, we know that fmap is the same as map for list, but we're not going to use map. We're going to make it a bit more difficult. Anyway, we always start our instance definition with instance functor and then our list type, where so we have fmap, and now we need to define fmap. All right, so we can think of a few cases. If we have an empty list, okay, we could define it as fmap equals map, right? No problem, but we don't want to do that. Let's define our own instance. So if we apply fmap and we get a function and we get an empty list, we can say I don't care about the function because the result is going to be an empty list anyway. Okay, the other case is when we get a function and we get some list xs, or we can use the pattern matching to get the head of the list xxs. And then what do we want to do in this case? So we want to apply the function to the head of the list fx, and we want to join it, so using the cons constructor, with the recursively processed tail of the list, right? So we call fmap with the same function on xs. And so eventually we can insert the... I thought you cannot use type signatures in the instant declaration, but I guess you can. Let's see. Anyway, eventually this will hit the base case of an empty list because we are removing one element by one from xs. I mean, we're passing the tail to the next iteration always, which has one element less. And so at the end it will be constructed and we'll get a new list with the function f applied to each of the elements. So let's try to reload this, okay? And now if we do the same thing, fmap, now it works, right? So we take the function times 2, which needs one more argument. That argument is going to be each element from the list. And so we get 1 times 2, 4 times 2, 2 times 2 is 4, and 3 times 2 is 6. Okay, so that works. What else do we need to check? We need to check the functor laws, right? So we know the first law of preserving identity is, let's say, if we call this function id on our list 1, 2, 3, we get back the same list unaltered. And that's exactly what should happen if we map the id function to each element, which is exactly what happens. Nothing changes simply by the result of mapping. And the other law is function composition, right? Which said that if we map a composed function, so we'll compose two functions here, let's say times 2 as before, but before we multiply it by 2, let's say we add 1. Okay, so now we have a composed function composed of two functions. We apply fmap to the same list, let's say 1, 2, 3, and we get back 4, 6, and 8, right? So 1 plus 1 first is 2, and then times 2 is 4. That's for the first element. The second element is 2, so 2 plus 1 is 3, times 2 is 6, the last one is 8. Okay, that's the result we get, and it seems correct. So what we want to check now is that this is the same as mapping, so f mapping, so times 2, and then composed with f mapping of plus 1. So we want to put this in brackets, and now we should get the same result. which we do, right? So it doesn't matter if we compose the function first and then apply and then map this function over a list, or if we map the first function over a list and then the second function over a list, we should get back the same result, which we do. So functor laws are satisfied, and this is a valid implementation for the list functor instance. Now let's go to the maybe type. So we already saw this functor instance definition in the presentation, but let's do it again here. So we have instance for functor of the type maybe, where we can get, so we have the fmap function, and it takes a function argument, right, and the maybe type. So we can first we know that the maybe type is equal to either just a or nothing, right? So we can consider nothing first, and in the case of nothing, we don't care about this function. We are just going to propagate nothing. And if we get another value, so we get an f, and then instead of nothing we get a just x, then we do care about the function because we want to apply that function to x. So what we return is just fx. So we sort of unpack this x, apply the function to it, and then wrap the result back into the maybe data constructor just. Okay, we can put the type signature here, which of course matches our functor general type signature. And yeah, that's the functor class for maybe. So if we reload this, we can map, let's just use the same function, so ×2, and then we have, okay, let's say we have nothing first. We get nothing back, of course. And if we have just 2, then we get back just 4. Okay, so mapping a function over a maybe type works. We need to check the functor laws. So if we map id over nothing, we get back nothing. If we fmap id over just 2, we get back just 2, nothing changes. Okay, and then if we have fmap, so composed +1 and ×2, we get back 6. And if we have the other version of that, which composes the two functions first, just 2, we get back just 6 as well, right? So these are equivalent, and those are the two functor laws satisfied for the maybe type as well. And with that, we can move on to the next type. Now, type 3, we have to define it. So in the presentation, we saw one implementation of a binary tree. We'll make a slightly different one here. In the presentation, the nodes which had children did not hold any value. So again, we can have a leaf node that carries some value a, and this is the same as it was in the presentation. But now what we had in the presentation is like a branch node that had two children, right? A tree of a and a tree of a. Now I'm gonna change this up a bit just so that it's not the same. Let's call the other one just a node and let it hold some value as well as have children, right? So our type now is exactly the same as in presentation, but the branching nodes also carry a value a. Okay, how can we make this tree type a functor instance? So we can write the instance as always, instance functor tree, where fmap is equal to something. Okay, so fmap receives a function. We can start with a simple case first, which is a leaf and the leaf carries some value x, right? So in the case of leaf, if we map a function over a tree and what we encounter is a leaf, then what we want to do is much like in the maybe just constructor, just wrap the apply the function to x and wrap it back into the leaf constructor, right? That's it for the leaf. And then if we have a type of a node, so the data constructor node, then we will have some value x, and we will have the two trees, left and right. So we can pattern match on the node constructor this way. And in this case, we want to return back a node, okay, that's for sure. The first argument to the node data constructor would be its value, but changed, right? A function applied to x, much like in this leaf. And then what about the left and right? So we'll have the node constructor needs two more arguments. The last two are two trees. So what we want to do is just recursively process the rest of the tree nodes. So we can also say fmap this function, that the same function, down the left tree, and fmap the function down the right tree. Okay, so that's the tree functor instance. Let's see if it works. So we reload this session, and we need to define a tree. Let's say my tree is equal to so let's just have one, so node with the value 1, and it will have let's just say 2 leaves, right? Keep it simple. Leaf 1, 2, and leaf 3. Okay, so we have our data structure, the tree, and we want to fmap some function over it. Let's keep to the same ×2, and if we map this over our tree, then we get an error because there is no show class for tree. So of course we know we can just do deriving the show class, which will give us a very simple show implementation. And now we can see the result. So it's node 2, leaf 4, leaf 6. So we see that every value in our tree was multiplied by 2. Okay, so seems like fmap is working for our tree functor, and we need to check the functor laws, of course. So if we do id on my tree, we get back just the tree as it was, and if we map it, we get the same tree. So the identity law is preserved, and the first law is fine. The second one, I'm going to just scroll up. The second one is, of course, function composition is preserved. So if we compose two functions, +1 and ×2, and then map the compose function over the tree, we get 4, 6, and 8, which of course we know is the correct result. So what we are interested in now is whether mapping the first function over the tree and then mapping the other function over the tree results in the same thing, and it does. So we know that both the functor laws are preserved, and this is a valid functor for our type tree. Finally, let's take a look at the IO type and how we can make it a functor. So IO is of course a bit of a different type because it's input-output actions, it's impure, it has side effects and so on, but it's still a functor in the prelude. So let's see how we can make it a functor ourselves. We have, as always, instance functor, and then we have the type IO where. Okay, so we need to think about what fmap means for an IO type. So we know IO types are actions. So, and we know the fmap first receives a function and then receives some type of IO, which we can pattern match as A, so it can mean action for us. We also know that with the IO type, we can use the do notation. and we know that the action of IO is going to produce some kind of a value. It could be even a unit, an empty tuple, but it's still some kind of a value. So what we can do when we think of mapping over IO is, how about we do this action, okay, and then get the value that the action creates and apply a function to that value, and then just return the result. So that's exactly what the instance, functor instance for the IO type does. And so we can have the do notation. We can say, okay, we get some x when we do this action A. And then after that, we can use our keyword return to wrap the result of f applied to x, right? So first we get the x, which is the sort of underlying, well, not the underlying, but the x is a result of performing action A. And then that result of that action, we apply the function to the result and we return it to make sure that we return a type of IO back, of course. Right, so if our function is A to B, then IOA, which so the x will be the type of A once this function has been performed. And then if we apply this function A to B to that x argument, which is of type A, of course we get back a type B. And then because of the return statement, return statement simply sort of wraps this value B into an IO type, right? Because we cannot go from impure to pure. So okay, the IDE is saying something. Why not use the infix operator for fmap? But we don't really care about that right now. I'll just leave it like this. And so let's check if our IO actions work now as a functor. In other words, can we map a function over an IO action? So what kind of function could we map over? Like let's say we're gonna use getLine. Okay, so getLine is a type of IO string or IO list of chars, and so we know on that type we could perform something like concatenation simply to list, and let's say append this to the end of the string, and we map this function on getLine, and getLine is an IO action. So what's going to happen is our action is now called. The terminal is expecting my input, so it's performing the getLine action. Once I give it some input, okay, let's just say some input. Once I give it some input and hit enter, that input is going to be saved in X, and then it's going to apply our mapped function on X and give us back the result, right? So we give it some input and we append this to the end of the string because that's our function. So that's how function mapping works over IO types. And of course we need to check the identity laws. So if we say get ID getLine and we enter test, we get back test. Okay, if we fmap ID to getLine and we enter the same thing, test, we get the same thing. So the identity law is preserved. And now we can do the function composition. So let's say our first function will be adding first, and the second function will be adding second. And we use it on getLine. We write test second first. Yeah, sorry, so I wanted to print first second, but of course the function to the right gets applied first, so we first add second. It doesn't matter. So test second first. What we want to check now is that, I'll use this, is that if we apply fmap, instead of applying 2 fmaps, we apply just one, but we compose the 2 functions, plus plus first and plus plus second, to get line, and we write the same thing, test, then we get the same result, right? So the second law is preserved as well, and that's the functor instance for the IO type. With that, we wrap our session on functors. So in summary, this video we looked at an introduction to functors and how they generalize the idea of function mapping, as well as took a look at some of the functor instances for various types. Thank you for watching and see you in the next video.